तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Let us now come to a specific integrated circuit chip, the configuration of which is given here. The exact values are not very important, which is usable for video or wideband application as well as tuned amplifier applications. We have already discussed that for a wideband configuration we would like to have a pair which is common emitter connected to common base. This any differential amplifier configuration of this type can be used for such cascode connection. So, how do we get a cascode connection in this is what we are going to discuss. So, T1 is actually the amplifier which is connected as common emitter here, and we will make this T2. So, that this is the common base amplifier. So, this combination T1 and T2 can be used as a cascode if, for example, I connect externally I connect VCC to this, so that this transistor may not come into picture in the actual structure, and here I connect the load. So, let us see, I connect here the load, external load. In the case of a wideband amplifier it is resistive, in the case of a tuned amplifier it will be a tuned circuit. So, this we will come to at a later date, right, VAGC, and I am going to short circuit this, so that this is the external connection, and let us say if I connect like this, then I can feed the input to the base of this. This is the common emitter transistor and this is the common base if I externally ground this by means of a capacitor. So, this is signal wise grounded by means of a capacitor. This is connected to VCC, and we see that if AGC terminal is left free, there is almost no current through 6K, and the base of this T2 is at the same potential as the base of T3, and therefore, these two currents will be very nearly one and the same. So, the current in this is going to be halved if VAGC is 0. Current is going to be halved, that means the gain is halved. Okay. Without this transistor the gain would have been GM into RC. So, minus GM into RC is the gain without the transistor, right. With VAGC is equal to 0, the gain is going to be halved. If now I apply a positive voltage here, so that the entire current is diverted to T3 and nothing is left for T2, then the gain is going to be 0. If VAGC with a certain positive value, I can make the gain go to 0. So, the gain varies from 0 to minus GM RC by 2 to GM RC. So, this VAGC therefore can be used to change the gain of the cascode structure. we had earlier learnt about the differential amplifier, and we have seen that as we apply a positive voltage here, the current gets shifted to this. As we apply a negative voltage, the current gets shifted to this. So, by applying suitable voltage, which we are calling as VAGC, we will understand why this is called AGC later. Okay. By varying this VAGC voltage applied at this point, we can therefore control the gain So, that is why it is called VAGC, gain control. Okay. GC, A means automatic. If this is permitted to be done automatically, we will see why such a thing is needed later, then it is called VAGC. But by applying an independent DC, we can see whether the gain is varied from 0 to GM into RC, right, minus GM into RC. So, you can therefore see that there is an advantage in this structure, that it can be used as a cascode with this conventional current source for the differential amplifier being used as a common emitter amplifier, and one of the two transistors of the differential amplifier being used as the output stage, the other transistor being used only for controlling the gain. Okay. So, this configuration is a very useful configuration, because in a straightforward cascode structure, if you want to vary the gain, you have to vary the emitter current. If you vary the emitter current, we have seen in the last class that Y11 and Y21 parameters also vary. If Y11 and Y21 parameters vary, then when we are using it as a tuned amplifier, okay, the Q, the bandwidth, all these things will vary. Whereas, this current remains constant, okay, and it is in this division of currents that is changed. So, that the parameter Y11 and Y21 remain the same, okay, when AGC takes place. That kind of advantage is offered only by this kind of structure. So, this is very popular in all tuned amplifiers. Where it may be coupled by means of an IF transformer at the input, okay, and a tuned circuit may be put at the output, which may be an IF transformer to the next stage. So, these are called tuned amplifiers, tuned at the input, what do you mean by tuned? That means resonant at a certain frequency called IF or RF, whatever be the frequency at which you want to design the amplifier, okay, that is called tuning, tuned at the input and tuned at the output. Now, let us understand what is meant by tuning. Let us say the input impedance of the cascode structure Y I is equal to Y11, because Y12 is 0. Because Y12 is 0, there is no interaction between output tuned circuit and input tuned circuit. Otherwise, it will be very difficult for us to tune the input independent of the output. Okay. Output and input will start interacting with one another because Y12 is 0. That means, the circuit is really unilateral. This we had discussed earlier in the beginning of the course, first part. So, in any tuned amplifier, it is necessary for us to have Y12 equal to 0. So, we can do independent tuning of the input as well as the output. What is tuning the input? Okay. Y I is equal to Y11, okay, but Y I total at the input is nothing but Y11 plus Ys, because this is the signal source. Okay. Tuning means making the real part of, that is making the imaginary part of Y11 plus Ys go to 0. This is what is called tuning, making the imaginary part of y 11 plus y s go to 0. This can be represented as, right, y 11 can be represented as g 11 plus j b 11 and y s can be represented as g s plus j b s. Okay. Then what is tuning? B 11 plus B s is equal to 0. This is the mathematical part of tuning. The susceptance of the input device plus the susceptance of the source is made equal to 0. If this is capacitive, then obviously this has to be inductive in order to make this equal to 0. So, this is what is meant by tuning. In such a situation, the entire y I total is going to be twice G 11, because G s is made equal to G 11. This is called matching. This kind of structure with matching at the input is done in order to transfer maximum power from the source to the input. So, maximum power transfer occurs due to matching when G s is made equal to G 11. Then y I total is equal to G 11, okay, plus G s, which is twice G 11. Okay. So, y I total at the input is twice G 11. Similarly, tuning at the output is to make B 22 plus, let us call this B L load, because y naught total is y 22 plus y L, total admittance at the load end, because again y 12 is 0, otherwise it would have been got affected by the input admittances. So, y naught total is equal to y 22 plus y L, B 22 plus y L is made equal to 0, and matching occurs when G L is equal to G 22 and y naught total at that point is equal to G 22 plus G L, which is twice G 22. So, this is tuning at the output. This kind of design is called conjugate matching. That is, total susceptance at the input is made equal to 0, total susceptance at the output is made equal to 0 by selecting the load admittance as conjugate of output admittance and source admittance as conjugate of input admittance. That is why it is called conjugate matching for maximum power transfer. Okay. Conjugate matching is done for maximum power transfer. So, given the parameters like this y 21, then y 11 and y 22, we can find out what is called as maximum available gain, maximum available gain, MAG. This is one of the important parameters of tuned amplifiers, power amplifiers, maximum available gain. Particularly if you are designing such RF power amplifiers as transmitting stage etc., you would like to use a device with a certain power gain called maximum available gain. What is the maximum available gain? Let us understand. The input is conjugate matched, so that the input source can deliver its maximum power to the input of the amplifier. Then amplifier amplifies with a certain power gain, and output load it is delivered by the amplifier when it is matched at the output also, conjugate match. Then whatever gain we get is characteristic of the amplifier that you are using, because you have optimized things at the input as well as the output, and that is called maximum available gain. Now, that is a power gain. Power gain by definition is nothing but voltage gain into current gain conjugate, right. So, if I have voltage gain expressed in terms of y parameters, which you can look back, voltage gain is y21, y21 is same as GM at low frequencies into RC, GM into RC. Y21 is replacing in this case of y parameters the GM. RC is nothing but 1 over y22 plus YL, and in our case that is the voltage gain. In our case y22 plus YL is really equal to 2G22. This is the voltage gain, and current gain is nothing but y21 again divided by y11 plus ys, that is current gain. Y21 is nothing but transconductance actually, which is nothing but input voltage, output current divided by input voltage, and y11 plus ys is nothing but input voltage by input current divided by input voltage. So, if you take the ratio of this, it is y21 divided by y11 plus ys and conjugate of this, right, current gain into voltage gain conjugate, or voltage gain and current gain conjugate, and this part is 2G11, and y21 conjugate is really speaking defined as y21 magnitude square. This is what is called as MAG. It is nothing but 4 G11 G22, y21 squared magnitude squared divided by 4 G22 G11 is what is defined as MAG. This is normally given by the manufacturer. If y21 is known, G11 is known, G22 is known, you can compute this, and that is the maximum available gain. This is normally expressed as 10 log y21 squared by 4 G22 G1. Right. Power gain, being power gain, it is in terms of decibels. Power gain in terms of decibels. And suppose, let us say, you are asked to design an IF strip whose gain is 30 decibels, and you know that you have a device whose MAG is 20 decibels, then you know that you have to use more than one stage in order to get for this IF strip a gain of 30 decibels, right. You have to use more than one stage, because single stage active device which you are using, this cascode device, is giving you only 20 decibels. So, this is very useful for deciding as to how many number of stages you must use in your system in order to obtain the desired sensitivity for the receiver, whether it is radio receiver or television receiver, right. And the sensitivity of the receiver is always determined primarily by the IF strip, how good your IF strip is. So, this part of the design is going to involve only these things: tuning at the input, tuning at the output, and evaluating the maximum available gain. Okay. And please note that in this arrangement, this current is going to be divided by VAGC. Okay. If VAGC is 0, it is divided equally. If VAGC is large positive, then most of the current goes here and nothing goes here, and the gain is 0. If VAGC is negative, most of the current can be diverted to T2, and therefore, the gain is going to be the highest as given by this. So, the gain can be controlled by VAGC. Now, how the gain is controlled by VAGC is very simple. This potential, if this is, let us say VCC is 12 volts, this potential is going to be very nearly half, because 3K is put. Of course, it is going to be slightly different from half because of this 0.6. So, it is around 6 volts, okay. And therefore, you will see that for VAGC of about 6 volts value, the gain is going to be half the maximum. Okay. When VAGC is coming down to 0, okay, most of the gain goes to this, right. This is 0, therefore, this is at a positive potential and this is at a lower potential, and therefore, all the current is diverted to this. So, the gain is maximum when VAGC is 0, when VAGC is 6 volts, gain is half GMRC by 2 or whatever it is, and then when VAGC goes positive, okay, by some value, then the gain can become very low. Okay. We can actually find out what is the variation in VAGC in order to create the required variation at this point from base to base, in order to divert the current from here to here. Now, that part of it can be easily evaluated, because we have seen earlier that if this is IE1 and if this is IE2, let us say, and this IE3 we will call it, this is IE1, IE3 plus IE1 is nothing but IE1, or this is actually 2, we will put it, this is IE1 equal to IE1. IE3 plus IE2 is always equal to IE1, and IE3 and IE2, they are governed by IE3 is IE naught, okay, into exponent, okay, VBE3 by VT. IE2 on the other hand is IE naught exponent VBE2 by VT. So, IE3 by IE2, the ratio of the two current is governed, okay, by exponent VBE3 minus VBE2 by VT. Now, what is VBE3 minus VBE2? This voltage minus this voltage, which is the voltage across 6K. So, this can be written as VBE3 minus VBE2, the voltage across 6K. And voltage across 6K is governed by voltage VAGC with an attenuation factor. Okay. So, voltage across 6K is governed by how VAGC is varied. Now, IE3 plus IE2 is the total current IE1. Now, out of this total current IE1, let us say 10% is IE2 and 90% is IE1 or IE3 and 90% is IE2, or vice versa. This is 90% and that is 10%. Why we take 10 and 90 is because this is an exponential relationship, and we cannot say 100% and 0%. It occurs at infinite voltages. So, we consider when it is 10% here and 90% here, or 90% here and 10% here, as the voltage swings necessary here in order to switch these transistors completely to off or on. So, in this case, then the ratio with exponent V6k by Vt equal to, let us say, 10 by 90 one case, exponent V6k prime by Vt as 90 by 10 as the range of V6k variation, which will cause the required change of gain from 0 to 100%. So, if this is divided by the other, one is divided by the other, we get V6k minus V6k prime by Vt as being equal to 81, or V6k minus V6k prime is equal to Vt log 81, which is equal to 109.86 millivolts. So, you can see that if I am to control the voltage here, the change in voltage necessary at the basis is about 110 millivolts, approximately equal to 110 millivolts. V6k prime minus V6k is equal to 110 millivolts. Okay. So, this is the change, that since it is the change, it does not matter whether it is one voltage change or the other voltage change. Okay. So, this is the change in voltage across, we will call it as delta V6k needed, that is equal to 110 millivolts. For any such differential amplifier, this is very clear. Okay. Then what is the change in what is delta VAGC for this circuit? Let us work it out. If delta V6k is 110 millivolts, what should be delta VAGC? These two voltages, this is V gamma, this is VCC, they are constant. Their contribution here is of no significance, because that is a constant contribution. We want, when this is changed, what is the change in voltage? That means, it is enough if you consider only delta VAGC here. Delta VAGC is going to result in an attenuation. There is a 6k, 12k and a 6k, and from here to ground we have 3k parallel 3k, that is 1.5k. So, the change is across 6k divided by 6 plus 12 plus 1.5, that is the attenuation factor. Okay. And delta VAGC is going to be attenuated by this extent, and that is delta V6k. Delta VAGC into this factor, this is 6 divided by 19.5. Okay. So, if delta V6k is 110 millivolts, then delta VAGC is 110 into 19.5 by 6. How much is that? Millivolts. About 300 and odd. 357.5 millivolts. So, that is the change that is required at, in order to change the gain from 10% to 90%. Okay. That is the change that is required. That will be useful for our design. Now, where is this VAGC used? You know, in all your receivers, because of the weather conditions and all that, because the transmission takes place through ionosphere, there are what are called E layer, F layer, etc. Because of some reflection there, the short wave transmission takes place. And suppose there is a receiver that receives signal, the signal level at the receiver keeps on changing, fading. sometimes it is very strong, sometimes it is very weak. If such thing is amplified by our amplifiers, sometimes the amplified signal is too strong for the power amplifier. So, the power amplifier may get distorted, okay, and sometimes it is too weak that you can't hear anything. So, this effect is seen as fading, right. So, the output you will hear very clearly, then at next moment you may not hear. This has to be prevented. How to prevent this? That when the signal level is low, you want the IF gain to be high. When the signal level is high, you want to purposely reduce the IF gain, so that the output to the power amplifier remains constant, right, drive, so that distortion is not there. This is what is called automatic gain control. This should be done by finding out what the IF gain should be. So, that can be found out from measuring the IF amplitude itself. So, in the detector you can actually get a DC proportional to the IF amplitude, okay, and that DC is made to control this current, okay, division here, that is this VAGC. That DC that you obtain at the detector is the VAGC, which will control all the gains of the IF stages as well as RF stage. If there is a communication receiver, that is fed to the RF stage also and also to the mixer. So, all these gains are controlled by the DC that is obtained at the detector. So, that is why it is called automatic gain control. So, your circuit functions very satisfactorily without this irritation about fading only when your AGC is functioning satisfactorily. This is also called automatic volume control, AVC or AGC. Okay. Automatic, okay, volume control or gain control. So, you will see that this is a must in all receiver design, and that is very conveniently applied here. So, that your parameter y11 and y21 do not vary, because this current remains constant. In a regular Cascode structure without this arrangement, these parameters vary and this gain also varies, because AGC is necessary, this current varies in order to vary the gain, then automatically the parameter varies, detuning also gets disturbed. Whereas, in this current remains constant as AGC voltage changes, and therefore, the parameter y11 and y21 never change, okay, and y22 also does not change here, okay, because this reverse bias voltage does not change because of the coil here. So, this is a very nice structure for a mixer stage or an RF stage or an AF stage, depending upon the frequency of interest to you. So, correspondingly a tuned circuit at the input and a tuned circuit at the output can be put. If it is an IF stage, this is IF and that is IF. If it is a mixer stage, this is IF, but this is a mixture of local oscillator frequency as well as the incoming frequency. The incoming frequency can be given here and the local oscillator frequency can be given here, because this acts as a multiplier or a modulator, and therefore, it is also used for a mixer. It can be also used for amplitude modulation, okay. It can be also used for balance demodulation, okay. So, this is a very versatile circuit. It is only dependent upon what kind of load, okay, and inputs you use, okay. The function is a gain control. Now, that we have seen clearly how a wideband stage can be used for tuned amplifier, tuned RF amplifier or tuned IF amplifier, depending upon the center frequency, you call it RF or IF. Okay. Now, IF is a fixed frequency amplifier, RF is a variable tuned amplifier. So, it is difficult to design RF stages compared to IF stages, and that is why most of the gain of a communication receiver is packed in IF rather than in the RF stage. RF stage has to work satisfactorily over a wide range with narrow band, and it is fairly difficult design. Now, these wideband pairs let us discuss. One was already cascode, common emitter with common base. Again, if you use common collector, which is by itself a wideband structure, common collector feedback structure with common collector with common base, which is also a wideband structure. This is a feedback structure we have understood, complete voltage feedback, this is complete current feedback, both of which are wideband structures by themselves compared to common emitter. So, common collector, that means collector is grounded with common base. Let us see what happens. If Vi is applied here at low frequencies, Vi, this Vi is now going to be applied across Re here and Re here, twice Re. So, the current here, signal current is Vi by twice Re, this Re and in series with that common base Re. So, the current in this is going to be Vi by twice Re, and therefore, the voltage across this is going to be Vi by twice Re into Rc. Which is strictly speaking Gm into Rc by 2, Gm into Rc by 2. A common collector, okay, is a high frequency structure because it is a very good voltage controlled voltage source. Here the load is made very nearly equal to the source resistance. So, that is why we have lost in terms of gain by a factor of half. Okay. So, the impedance level here is Re, if there is a capacitance, this Re is very small and it is shunted by another Re on the other side. So, Re by 2. Okay. So, it is very low. So, the time constant here is very low. Okay. So, the time constant at this intermediate point is very low. Okay. This is common base anyway, this is Rc and Cb dash C. Okay. That time constant also is very low. At the input here, normally it is driven by means of a voltage source because it is a voltage controlled source. So, source impedance is supposed to be very low. So, capacitance of common collector stage also is very nearly C B dash C because this capacitance does not come into picture much, right. So, the capacitance into Rs, which is very low, low time constant, low time constant, low time constant. That means, this is a wideband structure. Okay. Just like the cascode, this is a wideband structure. Only thing is, it is not equivalent to cascode because this voltage is halved here and appears in the same polarity because it is a common collector stage, and there is no phase difference between this and this. Therefore, there is no phase difference between this and this. So, this is not equivalent to common emitter stage or cascode stage in terms of low frequency gain, because there is a phase shift in the case of common emitter as well as cascode stage of 180 degree. That phase shift is not there, but this is a wideband pair. Okay. So, this also can be used for wideband amplifier design. Now, how is it used? Let us look at the same IC that we had. This collector of, let us say T3 is now connected to VCC, just like previous situation, and then you can put the load here RC, and now this is strictly being used as a current source. This is a differential amplifier, let us say, but that differential amplifier can be used as a common collector cascaded to common base in the following fashion. All that you forget about. So, you will now give the input at this point, right, and you will ground this point to ground through a capacitor. So, this is acting as common collector. Collector is connected to supply and half the voltage will appear here, and this will act as a common base and across. So, this is going to be strictly used as current source. So, the same structure that we had discussed earlier can be used as a common collector with common base, not as a cascade in the following manner. Okay. Please remember, this should not be connected to RC, then it is not common collector, it is going to be common emitter. Differential amplifier it will be. This is not a differential amplifier, this is a common collector stage with common base. So, is that point understood clearly? So, this is another wideband structure which can be used, but this does not have that disadvantage of AGC etc. and Y parameters not varying etc. Y parameters will vary as I naught varies, okay. And that therefore, if it is a fixed frequency, okay, amplifier without a requirement of AGC, okay, this stage can be used, wideband structure for tuned amplifiers, or it can be straight away used for video amplifier where you do not apply the AGC. This AGC terminal is not used, okay. So, you do not connect anything there. So, this is one way of using this as a video amplifier, okay. Next structure, common collector with common base, okay. Common collector with common emitter. Let us see this. What is the logic behind this? If we just use common emitter, we know that the Miller capacitance comes into picture, and the Miller capacitance will increase the input capacitor, and this input capacitor into input resistance parallel source resistance is what is going to constitute as the time constant. Here I am putting, if RS is pretty high, let us say RS is not very low, if I directly connect RS parallel RB dash E is going to be shunting the capacitor. If I put it through a common collector stage, then okay, this is still RB dash E parallel. Now, RE plus RS into 1 minus alpha, right, is the impedance that is shunting this. So, the time constant here is decreased, that is by artificially making it a better source than before, better voltage source than before by using a common collector structure. Okay. So, in case RS is very large, this technique can be adopted in order to use this whole configuration as a wideband structure. The gain here remains the same as that of the common emitter, okay, GM into RC, because the gain from here to here is unity and from here to here it is determined by common emitter amplifier. So, the gain is still minus GM into RC. Okay. So, for these two things, gain is remaining the same as common emitter, here it is halved. Okay. So, this also is a wideband pair. All these three wideband pairs can be used for high frequency application of video amplifiers. Okay. We have, apart from this, negative feedback amplifier stages with local feedback, okay, used for wideband application. This I have already discussed earlier. Okay. These stages, which are negative feedback stages, necessarily must be having simple poles. first order or second order folds, so that they do not go into oscillation. So, such structures are the following. This we have earlier discussed, that is Z feedback and Y feedback. This we discussed in detail in negative feedback amplifier. These are wide band structures. This is a voltage controlled current source, voltage controlled current source, and this is a current controlled voltage source. By connecting this like this, it becomes a wide band voltage controlled voltage source. This also has been discussed earlier, and the gain of this is RF divided by RE. Please refer back in your notes of wide band amplifiers, and this is a wide band amplifier voltage controlled voltage source. If you want a wide band amplifier current controlled current source, then you put this first, and then this next. This is a wide band current controlled current source. So, you have this individual thing which is acting as a voltage controlled current source, and this individual thing acting as a current controlled voltage source, and this cascaded together also is a wide band structure which is voltage controlled voltage source. These two cascaded together will again give you a gain of RF by RE for the current I naught by II here. This is V naught by Vi. So, this is going to be a current controlled current source, that is voltage controlled voltage source, and the individual things are voltage controlled current source and current controlled voltage sources, which are wide band structures, which are used all over for video amplifier, applications, and these ICs are available as video amplifier ICs. Only thing is, you can convert these structures, for example, into an IC by simply converting this stage into a differential stage. For biasing purposes, this whole IC can be converted into a differential structure. So, I would just want to indicate that for biasing purposes, you have to put a resistance from here and a resistance from here to VCC. So, this is RC2, this is RC1, and I just want to indicate how this can be converted into an IC without using capacitors, bypass capacitors, etc. So, let us convert this. I am connecting here RC1, RC2, then VCC. I put another identical stage here, RC2, VI1, VI2, RE 1, 1, 2, 2, all are identical. Then I want to convert this into an integrated circuit. The basic principle is, whenever you have a symmetric structure like this, the ground, this is the common point, can be lifted and you can make it go through a current source. I naught A, I naught B minus VE and plus VCC. So, this becomes a wideband IC. So, these current sources once again can be obtained by using current mirror techniques which we have talked about. Okay. So, again these can be represented by transistors. And it can be obtained by our current mirror technique or whatever it is. So, R 0 0, R 0 1, R 0 2 currents can be in terms of the resistor ratios. Okay. Therefore, this becomes a video amplifier stage usable for very high frequencies of the order of few megahertz. The gain of this, okay, differential gain is going to be RF divided by RE, RF by RE, if you take the differential output to differential input. Okay, this RF1 RC2 equal to RC1. So, that these are identical. Okay, I think there is one more resistance that is put. This will be RC2, this will be RC1. So, this is the symmetric structure which is going to give you a gain of RF1 by RE1 wideband.